Hello and welcome to another installment of OS from Scratch. In the previous video, we've written the code to turn on the LEDs on the Orange Pi 02. All we have to do now is compile and run it. How hard can it be, right? Of course, right off the bat, we've run into a problem. If we use GCC to compile our code, we're going to get an executable for Linux on Intel PC. We need... Come to think of it, what do we need? The CPU part is easy. The Pi runs on 64-bit ARM. Obviously, we need a compiler that can generate code for that platform. It would be much more convenient for us to compile the code for our new, as of yet nameless OS on the same computer we developed the code on. Since most of you viewers are not running on the new ARM-based Macintosh, that means just using our usual computer will produce code for the wrong CPU. Thankfully, there's a standard solution. Though this way of looking at it is a bit confusing, a compiler is just an algorithmic program that transforms data, the source code, into other data, the binary program. This transformation did not happen on the same platform as the one that's supposed to eventually run the code. There is a name for running a compiler on a different platform than the one for which we're compiling. It's called cross-compilation. So what we need now is to obtain a cross-compiler for 64-bit ARM. The name of the 64-bit ARM platform is AART64 for no apparent good reason. A quick search of our Ubuntu repository and we find a cross-compiler that might work. G++ AART64 Linux GNU. G++ is, of course, the C++ version of the GNU compiler collection. AART64 is the CPU name. The three words, AART64 Linux GNU, are part of what's called the target triplet. Technically, the triplet typically contains the vendor hardware platform, which is not part of this set. Our triplet also bundles into the operating system part the runtime library name, hence Linux GNU, rather than just Linux. The reason the vendor's name does not appear is because it doesn't actually matter. Once this runs inside the OS, all variants are pretty much the same. Of course, had we been compiling our own, we'd have specified the specific CPU submodel in use, in our case, the Cortex-A53, to get slightly better optimizations out of the compiler. What we see here is a preference to giving you a standard precompiled cross-compiler that works over something very optimized, but which you'd have to build yourself. So the CPU match is probably good enough, but this compiler compiles for Linux. This cross-compiler isn't a particularly good match for us. What can we do? One option is to compile our own version of GCC. While doable, and we'll definitely get to it later on in the series, right now there are two problems with this approach. One, it would take too much time to explain, and two, it would require us to decide what our target triplet, and thus the OS name, should be. While we might be able to squeeze one in, two is way beyond what we can handle at this point. As such, there's no other choice than to make do with what we already have. We'll take it one step at a time. We'll compile the code using the compiler we do have and worry about the rest later. First, let's install the compiler. And we can now compile using the command line AART64 Linux GNU G++. I hope you can spot the pattern developing here without me pointing it out. Let's go over the command line to understand it better. -O2 turns on compiler optimizations. -C tells the compiler to compile but not attempt to link our code. -G turns on debug symbols generation. While the final code will not contain them, they will be useful for us in the intermediate stages. No exceptions tell the compiler not to generate exception handling code. Exceptions require runtime library support, which we cannot provide, at least yet. It's better to just ask the compiler not to produce it. No stdlib tells the compiler we will not be linking with the standard libraries. This, and the next one, freestanding, is what allows us to use a compiler built for an operating system different than the one we're actually compiling for. We essentially tell the compiler not to rely on anything that would cause the code to depend on Linux. Last, but by no means least, we provide the name of the actual source file. And it doesn't compile. I've used a couple of types that are part of the standard C++ library, but not part of the built-in types. IntPTR-T, which I've misspelled IntPTR in the previous video, is an integer type that is guaranteed to be wide enough to hold a pointer without losing information. Int32T is an integer type that is precisely 32-bit in size. Having had a second look, we actually need uint32 here, an unsigned type, as we're accessing bit fields. Both those types require including, directly or indirectly, stdint.h. You might be wondering at this point, how come I can do that? How do I know that stdint.h doesn't require some weird support from Linux or the runtime library or something else which our new OS will not be able to provide? This question ties directly to another question which I've left open in the previous video. Why is it okay to use C++? I promise an answer is forthcoming. Not in this video, but soon. I've not forgotten. With that, I will address another question that, unlike the C++ one, was actually raised by about 5% of my viewers, so 1%. Why don't I write in assembly? And the answer is, why would I write in assembly? C++ is more convenient and more portable. I write in assembly when I positively have to. All other times, there is simply no upside. With modern CPU architectures, hand-coded assembly is actually less optimized than compiler-generated code, unless you invest insane amounts of effort. With that said, when writing an operating system from scratch, completely avoiding assembly is simply impossible. For this channel, some assembly is required. Hey, that has a nice ring to it. Let's make that the name of the project. I hereby change the name of the channel to Some Assembly Required. Let's call the operating system itself Saros. With the serious impediments out of the way, let's handle the trivial stuff, like actually compiling our code. And it compiles! Huzzah! We can see that GCC created a file called leds.o. The file command looks at the file and tells us what it is. Let's try to analyze what it tells us about leds.o. ELF, or executable and linkable format, is the file's format. Almost all modern Unix-like systems use it for executables and libraries. For completeness sake, I'll mention that Windows uses a format called Portable Executable and is typically marked PE. LSB means that this file is in least significant byte first format, aka Little Endian. I'll probably talk about endianity later on in the series. Relocatable means the file has metadata that knows how to change the address at which the code in this file is loaded. In other words, it has not yet decided where it is going to be placed in memory. ARM AR64 is our target CPU, of course. We can actually gain some insight into the file with the objdump command. As usual, we need to prefix the target triplet to it. -x tells objdump to tell us which sections are in the file. That deserves a word of explanation. The compiled source produces data that go into different sections. For example, global variables go into a section called data. Constants go into a section called RO data, or read-only data. The actual machine language goes into a section called texts, for reasons that seem to have been lost to the mists of time. Since our program uses no global variables, we can see that the data section is empty. In fact, keeping the number of sections to a minimum is precisely why I turned on optimizations so early in the process. Objdump can also be used to see the actual machine code produced. -d will give us a disassembly of the code. -s will do the same, but show us the source code that produced each assembly line. We can see that the compiler produces machine code that runs counter to our intuition. Effectively, our source code contains just 2 lines that actually do something, the 2 assignment lines. These are the assembly commands participating in setting PCCFG1. These are the commands participating in setting PC.dot. The compiler seems to produce code that constantly jumps between doing one and the other. The reason the compiler does that has to do with CPU architecture and optimization, and is beyond the scope of this video. I will point out, however, that making sure such optimizations don't break our code is why we used the volatile keyboard when we wrote the code. I will also remind you that, long term, volatile is the wrong solution, and there are better ones. The .o file is called an object file. It contains our program, already compiled to machine language, as you can see, but not yet set up to run from the correct memory addresses. That's okay, as the file is relocatable. We can still change the address at which it will eventually load. An object file will also contain dangling references to functions defined elsewhere, but used by this file. We can actually get a list of all symbols defined by this file, as well as those used by this file and defined elsewhere, with the nm command. Of course, Since we're asking for a file that belongs to a different architecture than the one we're running on, we need to run the cross-compile toolchain version of nm with the target triplet prepended to it. Pattern, right? The capital T tells us that this is a symbol our file defines in the text section. In other words, what we have here is a file that defines a single function. The lack of other lines suggests that it uses externally none. The symbol is a little hard to understand because of C++ name mangling. I've placed a link to a Stack Overflow answer I've written that discusses it in the description below. While you're already staring at the bottom of the video, you might as well click like and maybe even subscribe. To make things clearer, we can pass the -c flag to nm. This causes nm to perform C++ demangling, which means restoring the symbol to a more human-readable form. We can see that the symbol represents a function called LEDsOn that accepts no arguments. Surprisingly, that matches with what we actually defined in our source program. It's nice how, occasionally, reality fails to let you down. The next step we need to do is to link the object file. Of course, our object file doesn't use any external symbols. Linking is, however, still generally a required step. The reason is that certain aspects of the code are only resolved in the linking stage. Specifically, until linking is done, the code does not know at which address it is going to run. Linking is done with the ld command. Of course, we're going to need a cross-compiler version of it, yada yada yada. For a typical Linux executable, linking requires a fairly complex command line. Certain libraries provide support for compiler features, others provide platform support, and others yet provide startup and cleanup. For that reason, you seldom see people using ld to link. Linking is usually done via either GCC or G++. Those in turn call LD and add the needed support libraries. Giving enough command line options, we can convince GCC to not give those unneeded libraries. A better approach, in my opinion, is to just run LD directly. Linking actually succeeded, but the warning we received should not be ignored. The resulting executable is set to begin execution at our function, as if it had a choice, but at address 4000B0. We don't know whether that's the right address, and if it isn't, then things might simply not work. To understand what the address should be, we return to our trusty old H616 user manual. Searching for the word boot gives us the acronym BROM for bootrom. Looking at the table of contents, we find BROM documented in section 3.4. The H616 boot sequence is somewhat complicated. I won't go into the specifics, but suffice it to say that at its default configuration, and unless we start wiggling some pins, the Pi will boot from the SD card. Sadly, and I cannot stress this enough, the chapter on the boot ROM simply does not deliver what I believe it should. It is quite thick on boot types, but information on what one has to actually do in order to get your code to be part of the boot process is scarce, if not downright non-existing. It also discusses things such as secure boot and FEL without really explaining what those are. This deficiency is not rectified in the rest of the manual. Even our trusty Willis is no help. In fact, even after having managed to eventually run the code, I cannot find the key phrases and information in the manual. It simply doesn't tell you anything of use to getting our code to actually boot. Section 3.5, which comes immediately after the boot ROM section 3.4, does start with stating we have 32 kilobyte of static RAM at hex 20000, immediately followed by 192 kilobyte more. You would be excused to think this is related, but you would also be excused to think it is not. We just don't know. Sadly, not only does this state of affairs happen on other platforms, it is in fact quite common. Like I said before, the Orange Pi 02 actually fares better in that regard than others, which is why I chose it for this project. With the official sources of information lacking, we're left with no choice but to go to unofficial sources. Well, this particular source might be semi-official. I'm simply not sure. The linuxsunxi.org site is all about all sorts of information about all Allwinner chips. In fact, both H616 documents we showed came from this site rather than the Allwinner site. Surprisingly, the Allwinner site does not offer the H.616 documentation. The Linux SunXI page on the boot ROM has more information about addresses. The table there claims that the boot image for the H.616 is limited to 212 kilobyte and loaded at hex 20000. With that information, we can finally get to linking our LED's code. What we need to do at this point is let the linker know what memory it has available to it. The way to do this is by writing a file called linker script. We'll call ours fsl.lds. The FSL stands for First Stage Loader. U-Boot actually calls this part SPL, but as much as I dug, I'm still not sure why or even what SPL stands for. The first thing we need to do in the linker script is define the memory regions we have available. In our case, we have just one, 212 kilobyte of static RAM starting at hex 20000. We also need to define a few things regarding our output format, and we need to define the function at which execution will start. What we write here actually won't change anything, but for now let's write in _start, if only because that's what most other platforms are using. Next, we need to define the sections map. In essence, we write here which sections go into which memory. In theory, we can just say dump everything into SRAM. I'd rather not do that. There are several sections we simply don't need, and I simply don't want to pay the price for having them. I could just say discard anything unknown. This would work, but is a risky thing to do. If a section appears I was not aware of, that might indicate I'm using a language feature I don't support. I'd rather things break during compilation than during runtime. To resolve this, I like to define a dummy memory region called error. This region is 0 bytes in length. We'll direct all unknown sections into this region. This means that linking will fail with region overflow if we generate a section we're not explicitly aware of. It's not ideal, as it's very difficult to understand what section it was that made us fail, but it's better than compilation passing and then not running. In general, we prefer errors to happen as early as we can in the process. With that out of the way, let's direct the text, remember that's actually the code, the data, globals, and RO data, constants, to SRAM. We'll also make sure each section is 8 bytes aligned. Trying to link results in an error. I'll spare you the tedious comparing of which sections were generated versus which were specified by the linker script to quickly populate the list. Most of those sections are debug and metadata, which we don't need, so that's fine. One section isn't, however. EH-frame is used for exception handling. Despite our best efforts, GCC generated a section exclusively intended for exception handling. That sucks, but I found no way to make it not generate it. With a heavy heart and a sigh, we'll discard this section. And with that out of the way, linking passes and we have an ELF executable. Of course, we can't use an ELF executable. We want the raw code. Thankfully, there's a simple utility to do that called obj-copy. Just run it to create a copy of the file in binary format. That's what the -o means, of our ELF file into a single IMG file. IMG is just an extension I made up to signify it's a raw file. Indeed, if we look at the resulting file, it is small, uncharacteristically small. If we dump its contents through hexdump, we just get a bunch of numbers, which is not surprising. At first glance, if we compare those numbers to what objdump gives us as disassembly of the ELF, they seem totally different. A second look, however, shows us they are actually the same, except that each 4-byte sequence is reversed. That's actually what little endian means. With that, we're finally ready to write the code to an SD card and run it.
We're out of time.
No way, not again.
Sorry.
Everything's ready, just flush it and run.
It's going to take too long.
How? We're practically done now.
That's what you said the last time.
I'll grant you that, but I think we're pretty close now. We're definitely close, sir. At least tell me that we'll be seeing some LED action by the end of the next video. Well, maybe. Ah!